ELECTRA, how to train BERT 4 times cheaper. Reducing training flops 4 times by GAN-like discriminative task compared to Roberta 500K. So reading in our papers, this seems very useful for production. How much does it cost to train your language model? How much the trainings cost. It is an important part of machine learning production as the models get bigger. ELECTRA is available on HuggingFace, including model for pre-training. I personally haven't tried it, but it seems that everything is there. I think I will play with it in the future a little bit, because this is something that seems very useful. So why is BERT training inefficient, right? So BERT is bidirectional encoder representations from transformers. It's a transformer model. It uses unsupervised pre-training, and that's what makes it super useful, right? This unsupervised part, you just jam, you let flow lots of text through it, and using this unsupervised task, you can achieve good performance. So how does it work? So you take the text, you encode the text with a word piece tokenizer that replaces, pieces, basically compresses the text, replaces pieces, several characters with numbers, and then you can use those numbers in the model. In the model, you take the token number, you translate it into an embedding, 768 in case of a BERT dimension. You add some positional encodings, and then you apply these transformer layers. On the output, you can then do different tasks. You can do a sequence classification, you can do token classification, question answering, lots of other tasks. But what's crucial here is the pre-training, right? That's what we will be talking about in this pre-training part here. So how this pre-training works in BERT, probably familiar. So you have this input sequence, and then randomly you select 15% of the tokens, and you hide them from the model. So the model does not know, right, what was on that position. At the same time, you then ask the model at the end to give you a guess what was in the masked position. And the model tries to predict what is supposed to be there based on the local context. But the issue here is that every step in this training process costs us computation, costs us machine time. So can we improve the number of prediction that the model has to do? Can we instead of just 15%, can we do something with 100% of the tokens? Where do we get the difficult task enough for each position? How can we improve this? Well, that's what ELECTRA does, and ELECTRA, which was proposed in paper, pre-training text encoders as discriminators rather than generators. So ELECTRA is a shortcut for abbreviation of efficiently learning an encoder that classifies token replacements accurately. It's from Stanford and Google Brain. It was on ICRL 2020. It's not SOTA. But it improves this training speed. So what is the idea here? So the idea is that we want, for each position, we want to be able to learn something. How do we do that, right? So we add a new small generator, and which is trained on the original objective. It still trains on, we mask each position and tries to recover what was there. But the trick is that this generator is just a small part of the training process. What's important here is the generator replaces the masked tokens with its guesses, and those guesses are passed to the discriminator as samples. The discriminator is much bigger model. It takes on the input, the output of the generator, and the original tokens, and then it tries to predict, okay, on this position, is that original token or not? On this position, is that original token or not? Is on this position, okay, I can see there's something wrong here. For example, instead of cooked here, the cooked was masked. The generator for that position, it didn't know what was there for sure, so it tried to generate it, generated 8. And discriminator here noticed, okay, I think on this position there was supposed to be some kind of different word, so this word was replaced. So the discriminator detects true or fake. So this is not exactly GAN setup, because the generator is trained on its own task, so it's not trying to fool the discriminator. It works on its own task. So what's the exact architecture then? So the generator and discriminator have the same architecture. They share only embeddings and positional tokens. They try to share more between the two models. It didn't work in their setup, but there are some follow-up papers that do share more layers, even layers of the transformers. Here, only embeddings and positional encodings. The generator is twice smaller, or 4 times smaller. Bigger generator is not helping. We need to compute then more, and it also is. It seems to be that it's then becoming too difficult for the discriminator to see and to discriminate, to find what is and what is not generated by the generator, and then it ceases to be able to learn anything useful. Both models are trained jointly, because if the generator is too good, again, discriminator seems to fail to learn useful things, and at the same time, generator progressively, as it trains, it selects harder and harder cases. But it must not get too much better than the discriminator is able to see. So the loss function obviously is a sum. It's a sum of the language modeling for the generator and discrimination task for the discriminator for the bigger model. At the end of the training, we only keep the discriminator. Discriminator is the big model that we want. Generator is just a tool. So here on this graph, they tried various generator sizes, and usually the best results on clue score were for half or 1/4 size of the generator of the discriminator. So the results, datasets used were SQUAD, that's a benchmark for natural understanding. GLUE is a benchmark for natural understanding. Then we have SQUAD with question answering benchmark. And they mentioned two other architectures. So that's RoBERTa, which is basically BERT with training and dataset improvements. The RoBERTa uses longer training, bigger batches, more data. It removes next sentence objectives because it didn't help so much. It trains on longer sequences and dynamically changes masking pattern. I'm not sure what this last part is. I haven't read so much from this paper. ExcelNet is a BERT with permutation language modeling. It maximizes likelihood of the original sequence, likelihood of the original order, compared to all other permutations. And what log likelihood? Well, the likelihood in sense of next token prediction task. At least that's what I got from it. ExcelNet is at the time I think was very good model. So what we can see from the results down here. So from the results, what's crucial, why I said it's 4 times less flops. If we look at ELECTRA 400K, it's on par with Roberta 500K, but uses 4 times 5 less floating point operations. So let's look. Yeah, it's over here. We have Roberta 500K. Where is ELECTRA? That one is down here. They have a similar number of parameters, but the similar performance, but the flops for Roberta 500K are 4 times 5. Right. So this is for glue benchmark. That's the language understanding. There are various tasks here. The average is here at the end. And again, maybe just shortly, also the first column is the model, training flops, parameters. The next table gives us similar results. Again, Roberta 500K, similar results to ELECTRA 400K, but ELECTRA uses 4 times 5 less training flops. So this is the core, these are the core results. Why do we get this improvement? So they studied this in the paper. They modified the task to look what adds the most. And what adds the most seems to be that if we have loss for all inputs, that seems to be the core. So on this table, they progressively change the task, getting closer to the ELECTRA task. And they see improvement in glue score. So when they start with BERT task, they get 82.2. Then they try this replace mask language modeling, which instead of using mask language task, they replace the mask tokens with generated tokens. And they do get very, very small improvements. Then they do task that they call ELECTRA 15%, and they do discrimination over the 15% of the tokens. They get no improvement. So this is not. So if I understand this is not like the mask language modeling. This replacement is just basically using ELECTRA, but focusing only on 15% of the inputs. So yeah, so it's about as good as if you would just do this replace mask language modeling, right? So it's not about the discriminative task, because if we extend mask language modeling to 100% of the all tokens, if we do replace mask language modeling on all tokens plus copy mechanism, we get very close to the ELECTRA results. So again, what is this task? Is that you have also a copy mechanism that the model can guess if the token was replaced, it tries to recover it or guess if it's correct, and there is also this copying mechanism that it can also, for each input, it can guess if it's in fact, if it can just copy from the original sequence. So because the performance is very similar to the ELECTRA performance, which is also over all tokens, it seems that this having task over all tokens is the crucial part here. And also it tells us that like getting harder cases, basically getting sort of distracted by the generator, is not adding that much. That's just this 0.2 in this setup. Perhaps in more low resource setting this would be a bigger jump, but the biggest is just training over all tokens. That's what we can see from this replaced with copying over all tokens and ELECTRA results. Quick personal speculation. Maybe ELECTRA could be also suitable for raw resource setting because ELECTRA converges faster, perhaps. That would also mean that the less data is needed. That's something I will perhaps look into, think about more. There were some additional papers that are building on ELECTRA. So one of them is called BERT. It uses contrastive instead of discriminative learning. And so instead of saying, okay, this one was replaced or not replaced, the model tries to select from a couple of generated samples which one is correct, or if there was none, then say none. Another follow-up paper, also contrastive, but what was interesting about this one is that they shared more weights. So instead of just sharing embedding layers, they also share some additional bottom layers. This seems interesting, as intuitively I would expect that we can share more if we do it right. And it didn't work in the original paper, in the ELECTRA paper, but maybe there is some way how to do it correctly. Maybe the discriminator task. So both of these papers, they claim to improve a little bit. I haven't studied them too much. Okay, that's about it. Thanks a lot. If you have any corrections, I'm happy to learn new things. If you have any suggestions or good papers that you would like to hear about, let me know, and subscribe, and see you next time.